Hey, I'm Courtney Waterman, your tutor. Lover of anime, manga, and math. And you just tuned into another session of Tutor Me Sempai. Welcome back, everyone. Today we're jumping into an 8th grade topic, geometric dilations. Now, if you're new to my channel, I'll be putting time codes in for this video in the description box below. So use that to skip ahead to whatever part of the video you think is most interesting. At the end of this video, I'll be linking my 8th grade playlist, in which I cover a ton more topics. So if you're interested in that, make sure you stay tuned. As always, if you have any questions about what we see today, or even on homework, you can always put it in the comment box below, or visit me on my Facebook page at Tutor Me Sempai and tell me all about it there. Today's video will have 3 parts, so leave a like, smash subscribe, and let's get started. So far, we've covered geometric translations, reflections, and rotations. Today, we're going to be covering the first part of geometric dilations. Now, I say the first part because there's a bit we can cover here, but I want to break it up into multiple videos to make sure each part gets the proper amount of attention and we're not rushing anything. I want to really make sure you understand and you grasp it before moving on to the next step. Unlike geometric translations, reflections, and rotations, geometric dilations will affect the size of your shape. However, the orientation will remain unchanged. This means that your shape can increase in size, but it can also decrease in size. This process is very similar to whenever you go to the eye doctor for an eye exam. In order to see inside your eye, your doctor has to dilate your pupils. This changes the size of the pupils, making them a little bit bigger so that more light can go inside. This is going to be similar to what we do for our shapes. The dilation is going to cause the shape to change size, however, not just increasing in size, but also decreasing in size. And this increase and decrease in size is going to be controlled by something we call the scale factor. Now, the scale factor can have an unlimited number of values assigned to it. However, we're more concerned about the range in which the scale factor falls because that's going to determine whether your graph shrinks or whether it grows. So the scale factor can be one of the following, and I'm going to use a notation SF as a shorthand for scale factor. Now, this is not typical notation, but it's going to help me save some time. So the scale factor, or SF, can be greater than 1. The scale factor can be equal to 1. The scale factor can be between 0 and 1. So strictly between 0 and 1. And you can say the scale factor can be equal to 0. We don't typically look at scale factors other than these, so we're going to focus on these 4 here. However, even this list has some unnecessary parts to it. Scale factor of 1 and a scale factor of 0 is not going to give us much information, at least being useful for dilation purposes. A scale factor of 1 is not going to change the size of your graph at all. And a scale factor of 0 is going to make your graph go away, so you have no graph. So we don't typically care about these 2 types of scale factors, which leaves us with just these. A scale factor that's strictly greater than 1, and we have a scale factor that's between 0 and 1. So now that we remove the unnecessary parts from our list, let's figure out how these scale factors are going to affect your graph. So whenever you have a scale factor that's strictly greater than 1, that's going to cause your graph to grow. You're going to grow when your scale factor is strictly greater than 1, which means that when you have something between 0 and 1, you may have guessed it, is going to cause your graph to shrink. So this is going to be the overall behavior of your graph when you're talking about the scale factor. And remember, the scale factor is going to control whether your graph grows and shrinks and by how much. So before we get into our first example for today, let's figure out how exactly the scale factor controls your growth and your shrinkage of your graph. So let's say we've been given this type of information. We know the scale factor is going to be some value k. Now, it doesn't matter if k is going to be strictly greater than 1 or between 0 and 1. It's all applied to your point the same exact way. We are also given our initial point. So when you're talking about your graph, you're pretty much talking about a group of points. So this is going to be pretty much expanded to however many points you have on that graph. It's also really important to know where you're centered. So for this video, we're going to be focusing only on dilations centered at the origin. And because we're centered at the origin, there is a neat shortcut that we can take advantage of that is not going to be true when we're not centered at the origin. So assuming we have this essential information, we know our dilation is going to work in the following way, thus providing us with the very, very helpful shortcut. If you have a scale factor of some value k, your point p prime, that's going to be pretty much your transformation of p, is going to be the following: k x comma k y. So for any point on your graph, if the dilation is centered at the origin, you simply apply the scale factor to both x and y. The same exact way, the same k gets applied to both x and y. And the idea behind this is this scale factor is going to be multiplying your x and y to either grow it or shrink it depending on the value. So this is going to be our handy shortcut whenever we're talking about dilation centered at the origin. So let's take this and apply it to our next example. So let's say we have an example like this. We have this shape A, B, C, D, and we have to do a dilation with a scale factor of 2 on it. Now, because this 2 is greater than 1, we know that our shape should be growing in size. Let's apply our shortcut that we just figured out to this to see exactly how it's going to be growing. And remember, you have your point P, x, y, is going to give you your point P prime, kx, ky, where k is going to be your scale factor. And this is only because our dilation is centered at the origin. Now, your graph doesn't have to be centered at the origin, but your dilation, your transformation has to be centered at the origin. That's the only time that this is going to be true. So let's jump straight in. First, let's figure out what our points A, B, C, and D are. So A is going to be 1, 2. So 1, 2. B is going to be 1, negative 2. C is going to be 3, 2. So C, 3, 2. And D is going to be 3, negative 2. So now that we know our scale factor and we know our 4 points, let's find our A prime, our B prime, our C prime, and our D prime. So A prime is going to be, what do you get when you multiply this 2 by both this x and this y? So that's going to give you a 2, 4. Our B prime is going to be this 2 times 1, once again 2, but a negative 4 this time. Our C prime is going to be this 6, right? 3 times 2, and this 4. And our D prime is going to be, once again, a 6, but a negative 4. So now that we have our A prime, B prime, C prime, and D prime, we're going to be able to graph these. So this is going to be 2, 4, so 2, so 1, 2, up 4, so right around here. This is going to be our A prime. B prime is going to be 2, negative 4, so right around here. This is going to be B prime. C prime is going to be 6, 4, so 1, 2, 3, 4, 5, 6, 4, so right up here again. So this is going to be C prime, and D prime is going to be 6, negative 4, so this is 6 down here again. So something like this, and this is D prime. And then we just connect. So this is going to be our transformation, our dilation with the scale factor of 2. Notice the shape is still the same. We have the same rectangle, it's just a little bit bigger. We didn't get a square, we don't have a circle, we don't have a triangle, we don't have any other shape. We still have our same rectangle. So we've seen a scale factor that's greater than 1. Let's look at one more example to see a scale factor that's between 0 and 1 and how that's going to affect our graph. So in our final example for today, we're going to have this triangle ABC, and we're going to have a dilation centered at the origin with a scale factor of 0.5. This scale factor lets us know that our dilation should be causing our graph to shrink. So let's make sure that our shortcut is giving us exactly what we're expecting. The first thing you have to note is, where are your points A, B, and C? So A B, and C are going to be the points that you see here. And notice that C and B are going to lie on the y-axis. So point A is going to be negative 1, 2, 3, 4, negative 1. So negative 4, negative 1. So this is going to be our A here. Our B is going to be 0, 1, 2, 3, 4, 5. So 0, negative 5, right? And our C is going to be 0, 1, 2, 3, 4, 5, positive 5. So these are going to be our 3 points. So using what we know about our shortcut, let's apply our scale factor to our 3 points and see what our transformed points are going to look like. So we're going to have an A prime, B prime, and a C prime after we do this transformation. And whenever we apply this 0.5 to this point up here, negative 4, negative 1, we're going to get a negative 2, negative 0.5. Whenever we apply it to B, we're going to get a 0 because 0 times anything is going to give you 0 again. And we're going to get a negative 2.5. And for C, once again, 0, and we're going to get a positive 2.5. So now that we have our A prime, B prime, and C prime, let's graph them to see how they measure up to our original graph. So A prime is going to be negative 2, negative a half. That 0.5 is a negative a half. So we're really going to be like right in here. So slightly up in here. Our B prime is going to be 0 and a negative 2.5. So right in here. This is going to be our B prime, right? This was our A prime. And our C prime is going to be 0, 2.5. So pretty much right in here. So this is going to be our C prime. And we're going to connect these points. Looking at our 2 graphs, it does look like our dilation caused our graph to indeed shrink. Our A prime, B prime, and C prime triangle is indeed much smaller than our ABC original triangle. However, notice once again, the shape hasn't changed. We don't have a rectangle all of a sudden. We still have our same triangle. So this is what it looks like when you have a scale factor that's between 0 and 1. It indeed causes your graph to shrink. So I hope you have followed on to these examples, and I hope you see that if you're centered at the origin, you have a nice and easy shortcut in order to do your dilation. However, if you have any question about what we saw today or even your own homework, you can always put in the comment box below or visit me on my Facebook page at Tutor Me Sempai and tell me all about it there. If you haven't done so already, remember to leave a like. It really helps the channel by letting YouTube know that you found this video helpful. And if you found the video helpful, so can someone else. So leave a like, hit the notification bell, smash the subscribe button, and share this video with a friend. Well, that's all the time I have for today. I really hope it's helped with your homework. I'm looking forward to seeing you again next week. I'm Courtney, this is your playlist, and this has been another session of Tutor Me Sempai.